Oh, hi.
Didn't see you there.
So for our compression, we started off by taking our RGB image stack and converting it into luminance and chrominance channels. We then downsampled our data, twice as much for chrominance channels as luminance. We then fed it into pi wavelets, which we got wavelets out, single level, and then we removed the high frequencies for chrominance channels. We then fed it into our quantization algorithm, which would then compress in bit stuff our data into n bits per value. We would then reversibly compress all of our NP arrays containing our data into a bit stream. This is reversible, and then we would check to see if it fit within our bandwidth. If it did, we would send it. If it didn't, we would decrease the number of bits we use per value or downsample.
We also experimented with other methods of compression, including packing the data into characters and combining zero-run encoding with bzip2 on top of our wavelet scheme. This was competitive with our standard scheme, which used LZMA, but did not always yield improvement. We also tried using a different wavelet packet structure by pulling the data arrays directly out of PyWavelet's 2D wavelet packets, flattening them and then compressing instead of using the CoWoS method, performing SVD on the wavelet coefficients, differencing, and designing our own wavelets with a patch SVD scheme. For each of these methods, the improvement was marginal, so we did not integrate them into the final product.
After compression, we send the binary data through an AFSK 2400 modem with the mark and space frequencies set to 2.4 kHz and 3.6 kHz. A different packetization scheme was created to minimize the amount of overhead and transmission so that we can send out as much data as possible. The packet is led with an alternating series of ones and zeros to give the PLL a better chance to lock on before the data.
This is followed by packet number, total number of packets, and finally the data itself. The data segment is bit stuffed, verified with a 2-byte CRC, and can be of variable length, such that we can send something equivalent to a single stream if desired. To safeguard against the possibility of a few bits being flipped during transmission, we have a Reed-Solomon error correcting code applied over the data segment of the packet as well.
Alrighty, so we are transmitting from over there. Say hi. Alright. And we are receiving on this side, right here. Here on the transmitter side, we compress the data into a binary bit stream and then generate the audio for transmission. At the same time, at the receiver side, we record for 75 seconds. After recording, we can decode the packets. As you can see here, we receive all 9 packets successfully. With the received data now in a binary file, we can read this file, decompress it, and then play back the GIF.